an estimator, okay, and making adaptive. And so I mean, before coming, when I was walking, I said, why don't you really describe what you're doing? You really means myself, okay? So now I want to spend a few minutes to tell you what we are really doing, okay? Now, this detour is because I told you, I anticipated the adaptive filtering with respect to the Bayesian estimation. So this creates a little bit of mismatch, okay? So now, I try to cope with this mismatch by evoking your intuition. Now, so what I want to do is this, okay? So, just to say we were showing the learning curve, how to choose mu, how to scale mu in cases of need, okay? And then everything, the learning curve depends on the average eigenvalues, and so this is what we discussed. Now, I want to make a small remark, small but quite important. That page below here. Now, what we are really doing. Okay, so what is the adaptive estimation? What the adaptive estimation is really doing? So, the model that I was describing is the following. So, I have a signal xn, whatever is xn, and wherever is taken. Okay. So, this xn goes into, because this xn is a random process, also is a set of time-varying random variables. Now, this goes into an estimator, which is A. And A, what does A? A actually, is, I have this xn. This is the sequence xn. So I take, let me say, n naught. Okay? And I'm taking a set of samples. Let me highlight in this way. So I take this set of samples that might be causal and anti-causal, it doesn't matter, okay? So I'm using all these samples, okay, that are around here. So I don't know if this is the anti-causal part, and this is the causal part, okay? So I'm using all these samples. I'm calling this vector of samples as x vector n naught, just to remember where I selected these set of random variables. And then I'm using this one to estimate theta hat. So this theta hat, that is for the sample n naught. So let's put it n naught, okay? So this is for the sample n naught. That's wrong. N naught here. And this depends on A, a set of coefficients. Okay? That's what we did. Now, this is the most general because I'm taking a sequence xn to estimate theta hat. Okay? Now, what I'm doing further is that, I compare this one with another, the true theta. N. Now, at the same time, n naught. Okay? Now, this comparison might be, in general, might be instantaneous or statistics. Now, what does it mean? What is the difference? If it is instantaneous, means that, I stay on the sample, theta n naught, and then I compare sample by sample. And then in this way, okay, so if I take this minus the other, okay, so what I get an error. That is instantaneous, and this error depends on the set of coefficient A. Okay? So that's what we did. So it is instantaneous if I make a theta minus theta hat. It can be statistics if I take the expectation. Okay? So when I take the expectation, remember, we don't really need to have the samples. We need to know the statistical properties of the correlation among the samples. Please write this sentence. among the most stupid. This is the only sentence that you need to remember. Okay. So, by the way, we have a movie there. Okay. So see the movie again. Okay. So we can compare instantaneous samples, or if we don't have the availability of the instantaneous sample, we need to have the statistical properties of the comparison. And this is obtained by taking the expectation. So the adaptive system is taking the instantaneous value, because we don't have the statistical property of the correlation among the samples. And then, the statistical properties comes for free, if you like, comes for free by adapting the error. The ensemble one, okay, so if we don't know the instantaneous value, but we know the statistical properties, okay, that's fine. That's another way. So in this way, we can calculate, by knowing the statistical properties, we can find the optimum A, okay, so the optimum estimator. So it's out of any question that A is the estimator. Okay, so that's the setup. Now that we understood all that, let's look at again on the story that we don't use the instantaneous. We use the statistical property of the samples. And so now what we did the following. We calculate the error, and we made the error square that depends on A, and we took the expectation. Now when we make this, that means that we know we can do the expectation. That means that we know the statistical properties of the samples. What we did, again, we calculate the optimum one, so I'm moving now. We calculate the optimum one by finding theta, A hat, or A optimal, which is the optimum estimator, as arg min with respect to A of the error. Now, this one is the minimum mean square error estimator, because we are minimizing the mean square error. Okay? Now, when I say statistical properties, I'm saying that my expectation is taking the expectation with respect to x and with respect to theta. So we are assuming that theta and x are random process, or are stochastic variables. Now let's continue on this line, okay, with a little bit of conceptual and practical manipulation. Now let's rewrite the error. Okay. Now we know that the error is equal to, so it is theta n naught minus, so it is A transpose x n naught. Okay. This is the error. Okay. So when I write, the minimization of the error, now, let me calculate on a new page. So let me copy the error. I simply copy. And I paste in a new page. Beautiful, this story that I can paste everything. Okay. So here. So this is the error, so it is expectation of this one to the square, right? Okay. Now we have seen that developing, so this comes to be a quadratic form. With respect to A. Okay? We know that, and we optimize blah 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 blah. But let's do the same directly on that. So let's calculate now the derivative of the square of the error, and then we set the derivative to 0. So what I do now, I take the derivative of A of the error. Now let me copy. Okay? And let me set it to 0. Okay? Now, so let's make it. Okay, so I have the derivative with respect to a. So, you know, when I say, you already learned that. When I say that I calculate the derivative of, with respect to a vector, means that I calculate the derivative with respect to each entry of that. Okay? So that means that I have a square. So when I calculate the derivative is 2 times the error. Okay? So it is, the derivative is equal, is 2 times, then it is expectation of theta n minus a transpose x and, oh, it's n naught, okay, so it's n naught. And then I need to calculate the derivative of the inner part. So, you know, I need to calculate the derivative. Let me write this way so you get, it's more clear to you. It's the derivative with respect to a of theta n minus a transpose x n. Set to 0 again. But you know, this derivative, theta does not depend on a, so it goes away. But this one depends on a. So if I look at my table, I go at the beginning of the book, or you know, when we started, this is equal, this part is equal to x transpose. So perfect. So, you know, I just plug this into there. And then it comes out that it's minus 2 times expectation of theta n minus a transpose x n multiplied by x n, oh sorry, it's n naught, okay, n naught transpose equal to 0. Now, I need a little bit of space, okay? So now, you know, let's reinterpret this. So this one is the arrow. This is the arrow that depends on n naught, but also on a. So if I rewrite this equation is telling to me that, you know, it is equal, solution is equal to the expectation of epsilon n. Now, you know, I don't need to set a specific value of n because the process is stationary. So I can choose any arbitrary n, okay? So it's epsilon n that depends on a times x transpose n equal to 0. So this says that solution is obtained when the error, the product between the error and any value of x, any value into the vector of x, okay, the expectation is equal to 0. So this is the error, and this is, you know, you can imagine here that I have x1, x2, x3, x4, x5. So this is called orthogonality condition, orthogonality principle. So this is the most general one. So this one says that the solution is obtained, and the estimator is obtained, by setting the orthogonality condition between what? Between the error, you see the error, and what is x? Is the input. Okay? Because remember, you know, the system is this way. I have a, I have x, you know, but I mean I have a, and then, you know, I'm selecting a vector of x. Because I mean, this one is capturing a piece of x. And now, you know, this is theta n. So when I say that, you know, I'm taking the input. So I want to have the orthogonality condition between error and the vector, the data that it's inputting here. This is the most general solution. So this one is called, and you know, we give more theoretical framework a little bit in 10 days. Okay, so this is called orthogonality condition. This orthogonality condition is to solve any minimum mean square error problem subject to the linearity of the estimator. But you know, I mean, we don't say the linearity of the estimator, so it's enough we say it's a filter. So it's a filter, a linear, any filter is linear, okay? Because if it is not linear, we say it's non-linear filter. So by default, any filter is linear, unless we don't specify. So then I can say that, you know, the orthogonality condition is a general condition for any MMSE filter. Now we can make the exercise. Because I mean, this is the most general. Okay? This is the most general. So the goal today is twofold. You know, I make the exercise following this principle, so that you get practice on that. And you know, the adaptive filtering is simply solving these problems without the expectation, just to say in a very simple way, because it's simply taking the instantaneous error and correcting them. It doesn't correct. It doesn't, you know, compute the expectation. That's the point. Now, so this relationship, which is more general, is valid in any condition. So my goal, as I said, you know, I want to make a couple, 2-3 exercises, and then, you know, we make a break, and then we close today by making the second part, which is on recursive least square distribution. Okay? I told you it's a mix today, so with exercise and with closing the theory. Now I prepared some example. Okay. Now we look at this one later. Okay. Now, so let's start with the exercise. Okay. So this is taken from 6 February 2017. So you know it's almost 2 years ago. So let's read together the text. Now, we have two processes. Alpha is normal, beta is normal. Two statistically independent white random processes. So, you know, these are white random processes. The two corresponding signals generated by filtering, more specifically. Now, y is equal to 1/3 yn minus 1 plus alpha. So alpha is the excitation to an autoregressive process, okay? Because this is a recursive filtering, okay? And that's y. X, what is x? X is taking beta, and then, you know, is summing with y. So y, you know, is entering and summing to that. That's you know what we noticed. So now let's make it. I mean, this exercise is not different from the one that you saw for the intermediate exam. Okay, so you know, let's make it quick, very quick. Now, first, it says characterize the process of y and evaluate its autocorrection sequence. Okay, now what is a y? Now it's y equal 1/3 y n minus 1 plus alpha. So let me write in z transform if you don't see it immediately. Okay, so this one in z transform is yz equal to 1/3 z to the minus 1 yz plus z transform of alpha. Okay, so you know it is equal to, so yz, okay, is equal to az divided by 1 minus 1/3 z to the minus 1. So I will take alpha and I filter with one pole. Okay? So the process is autoregressive order 1. That's the answer here. And you know, if I need to know what is the autocorrection in this case, well, it's the autocorrection for the autoregressive process order 1. So you know, if I need to write, I write here because I mean we need it. Okay, so if I need to write r y k is equal to 1 minus 1/3 square, and then it is 1/3 to the power k. That's the autocorrection of y. Okay. If you don't know why, you know, go and see the intermediate. Now, what is the second one? So the second one, okay, xn. So xn is taking beta. So I have a beta plus 2 times beta n minus 1, then I have a some y. Okay? So no, let's see the block diagram. Make the block diagram in any exercise. Make it. It's helping you a lot. So I have alpha n. I didn't want to stand up, I need and beta n. So that one is filtering by one pole. And I get 1. Okay? And we know the autocorrelation for that. Here I have a filter. Now the filter is 1 plus 2 times z to the minus 1. Okay? Then, I'm summing this. Now when I sum, this is exact. So before summing, this is a moving average. And this one is autoaggressive order 1. But after that, it's not a moving average because it contains the other random process. So in order to establish that, I need to calculate, okay? I might calculate the autocorrelation for that, which is the autocorrelation is the sum of the autocorrelation for this plus the autocorrelation for that. Okay? So Rxk is equal to the autocorrelation of the moving average. Now, since this one is a moving average, let me call this temporary variable as Gn. So the autocorrelation of G are RGGK. Okay. Now, RGGK is obtained by computing RGGZ. Okay. Now, this is just a refresh. It seems that it's an exercise for the intermediate test, but this is what you need to know. So you need to get skilled to calculate that. So this one is 1 plus 2z to the minus 1 times 1 plus 2z. Okay? So it is 1. Then you have a z and z to the minus 1. So this is 4. So it is equal to 1 plus 4 is 5 plus. Then I have a z to the minus 1 times 2. And then, and then it's 2 times z. So it is 2 times z plus z to the minus 1. Okay, so this is the autocorrelation. So Rxx is equal to that one plus it's 5 times delta k plus 2 times delta k plus minus 1. Okay? Which means, it's the autocorrelation 1. This is the autocorrelation. Fine? Now, let's start the exercise of today. So, now the exercise says, by the way, x is R1. Okay? Now, the exercise today is the following. We need to solve numerically. Notice that without solving numerically A1 and A2, the remaining part of the exercise cannot be solved if not just qualitatively. Okay, so qualitatively means, you can write just the words. But since I'm asking you to solve the exercise, so words count a little bit as the outcome. So evaluate, forget about B for a minute, okay? Now, use a set of 3 samples, xn minus 1, xn plus 1, twist and make the sample alpha n as follows. Now, what am I asking? I am asking the following. So, x here, okay, you can look at X in the following way. X contains Y, but is affected by this G that is acting as a perturbing process. Because my goal is to estimate alpha. Okay? So now you know what I'm, let me copy here, so it's 1/3. Okay. So now, what I'm asking is, estimate alpha using 3 coefficients. So what I'm asking is, use a filter made by 3 coefficients. So the 3 coefficients are h minus 1z plus h0 plus h1z to the minus 1. That's my estimator. Let me say this estimator is h. Yes. So h is unknown. We don't know that estimator. Now, you might say, but what is the problem? This is a pole, so I set the 0, right? Look at the exercise in this way. So you have a block diagram, Imagine that I make a block diagram, and rather than make it this way, I make it this. I have 1 divided by 1 minus 1/3 z to the minus 1. And, and then I tell you, estimate that. Okay, so what you do? The filter is stupid, because, it's, this term will be 0, this one will be 1, and this one will be 1/3. Right? Look at here. I don't know. How can I do to show it? Oh, we already computed that, so I have room. Let's make this one. This is alpha n. This is yn. Now if there is no x, so if there is no g, then if I interrupt that and I need to estimate alpha, that means what is the filter that I need to put here is h such that here I have alpha hat n. What is the filter? Right? It's 1 minus 1/3 z to the minus 1. Okay? So the answer is coefficient h minus 1 is 0, coefficient h0 is 1, coefficient h1 is 1/3, minus 1. Do you agree with that? Okay? Now you know why this is not a filter. Because there is an additional term that I call the Gn. I have a noise. So this Gn is injected here as if it is a noise. And this noise says, if you make this way, the alpha that you get is not optimal. What does mean optimal? That the mean square error between this and that is not minimum. Okay? So I need to calculate, the filter in such a way that this alpha hat is minimum with respect to alpha. So now let's make it. Okay, now I have everything. Okay. Now, if this is the filter, it should come out from my analysis. If this is not, then we'll see what's happening. Is it clear, how I frame the problem? Now, once you get practice with that, you immediately say that. So probably this is the first time you see, and that's why I'm spending the time when you are fresh mind, which means you are fresh. Okay. So so we came out with that rule. So my estimator, which is h, okay, which is unknown, my estimator is alpha hat n is equal to a filter h, which is unknown, multiplying x. Okay. So this x is xn, xn minus 1, and xn plus 1. Transpose, forgot transpose. Okay? So that's my unknown. Now, so let me call this one as x factor at the time n, because I mean this one I have an x n, and is taking three values, okay, that are combined with the the vector h, which is unknown, to get alpha at n. If I call this n naught, this is n naught. Okay. So now let's write the problem. Okay. Now the problem is, what is the error? Now the error depends on the sector coefficient h, and h is the yellow, which means the unknown. So now the error is alpha n minus alpha hat of n. That depends on the sector coefficient a. Okay? Let me highlight the dependency here. Coefficient h, not a. Okay. Now so this depends on the sector coefficient h, unknown of the problem. Now, and this one minus h transpose x n. That's the error. Now, what we proved 5 minutes ago, we proved that the orthogonality condition is the optimum mean square error estimator. That is also the convergence of this mean square adaptive filter. Which is the same. So now let's impose the orthogonality condition. So the orthogonality condition says that I need to calculate the orthogonality between the error, that depends on h. I go and see the formula, time x transpose, okay? Equals 0. That's my unknown. Always keep present what is the unknown of the problem. Now, let's compute that. So now I take the orthogonality condition, and I expand the orthogonality condition. Now, so this is alpha n minus h transpose x n. Okay? So, you know, when I plug this into that, then I get the expectation of, I have alpha n x transpose n minus, it is h transpose multiplied by the expectation of x and x and transpose. Equals 0. So, you know, if I set equals 0, this is equal to the other. So, you know, what is this? Now let's analyze piece by piece. What does it mean, expectation of x and transpose? Okay, that one is expectation. Oh, now what is xn? Okay, xn is xn minus 1, xn plus 1. And what is x transpose? X transpose is the same. So xn minus 1, xn plus 1. Okay, that's the transpose. So, what is in the first position? Now, in the first position, I need to calculate the expectation of xn minus 1 squared, which is the autocorrelation of x calculated in 0. What is in the second position? So, in the second position is when xn is multiplied by xn, x0. Okay, here is the autocorrelation calculated with the leg 1. What is xn minus 1 with xn plus 1? That is the autocorrelation calculated in 2, leg 2. So, you know, I just now replace, so I mean, I simplify, so that this is rxx calculated in 1. Here is rxx calculated in 2. Then, what is the second? Is xn minus 1. So it's the autocorrelation calculated in 1. Then the other, xn is the power of x. Then the third one is xn plus 1. So it's the autocorrelation calculated in 1. That's right. rxx 0, rxx 1. Then the last line. The last line, you know, is rxx, that's the row, calculated in 2, rxx calculated in 1, rxx calculated in 0. Okay. So now let me make it compact. Okay, so this is rxx calculated in 0. Okay. So, by the way, you can also say, but you know, if you don't say, it's all the same, so it's not relevant, that this matrix has a structure along the diagonal that is all equal. So if the matrix has, you know, along the diagonal, you have the same entry, okay, is called that matrix is Euclid's structure. Okay, just a comment. Huh? Now, so I know what is this term. Okay, so I know they call this matrix as R. So I computed this term. Then I have another one. Now this is you know, a, let me manipulate a little bit with the space. Okay. So the second part is expectation of alpha is in row oriented. That is expectation of alpha and x n minus 1. Then it is alpha and x n. And then it is alpha and x. I'm shrinking, okay? It's not nice. Let me rewrite it so that you have it. So it is alpha and x n minus 1, alpha and x n, alpha and x n plus 1. This is the second part. So let's rearrange again. Okay. So I have, I copy here so you have in front. Okay. So I have a, I have a vector which is the row vector equal to H transpose a matrix. Okay. So I have a row vector equal to H transpose time matrix R. Okay. So I prefer to have the unknown. I prefer to have the unknown in a vector. So I transpose the left and right. So if I transpose the left and right, so if I make a transpose here, as I make a transpose there, what I get that R, in principle I have R transpose H equal to the vector, that one which is indicated at the top. I found a solution because I need to invert R. And once I invert R, I have a solution. But R contains the autocorrelation. And we already computed the autocorrelation because it's here. So we know everything about the problem. Now, we don't know the column. So how to compute the column? If we need to compute the column, okay, the column is alpha and xn minus 1, alpha and xn, alpha and xn plus 1. So is of the kind where I have alpha and x n minus or plus a value. So let's compute this term separately. So the vector is composed by terms where I have an expectation of alpha and x n minus L. Okay, where L is equal to 0, 1, minus 1. That's the term we need to compute. Now, what is xn? xn minus L. Okay. Now, xn minus L is equal to, I read now there, is equal to g n minus L plus y n minus L. I read there, okay? That's g, that's y. Then that one is computing, so I'm computing alpha n time, open the bracket, g n minus L. Let me say one by one. Plus expectation of alpha n y n minus L. Okay, simply put it there. Now alpha is here. So I need to calculate the correlation between alpha n and gn. But gn, it depends on beta. and beta is statistically dependent from alpha. So for this reason, this correlation between alpha n and gn, regardless of the delay, is 0. Okay? So this term is equal to 0. Okay? And what about the other? So here I have a yn. Well, you know, let's see what is yn. So yn is equal to 1/3 yn minus 1 plus alpha n, because of now the formula, okay? The finite difference formula. So that means that yn depends on alpha n. Okay? Yn minus 1 depends on alpha n minus 1. Yn plus 1 depends on alpha n plus 1. So let's put this information to the formula for the second part. So that means that yn minus L, this formula, okay, n minus L, is equal to 1/3 yn minus L minus 1 plus alpha n minus L. Then, by, this is just recalling the generation model for yn. And this is what I can say. So I can now plug this into there, and I can compute. So I need to compute just the expectation of alpha n. Then I have alpha n minus L. Then it is plus expectation of alpha n, then time 1/3 yn minus L minus 1. So, let's calculate one by one. So I need to compute for L equal 0. Now for L equals 0, I have here alpha n, which is the power of alpha. Alpha n, yn minus y minus 1. But yn minus 1 depends on alpha n minus 1. So since alpha n is uncorrelated, is 0. So for L equals 0, the only which remains is only the first one, which is, let me try to write a set of relationships so that it remains to you very easy. Let's put in column. Here. Okay. So for L equals 0, this is 0, and this is equal to sigma square alpha, which is equal to 1. Now, what about for L equal minus 1? For L equal minus 1, I have expectation of alpha n time alpha n minus 1, which is alpha n plus 1. This is equal to 0. What can I say to the second one? Now the second one is alpha n, and then I have yn minus n minus 1, which is n plus 1 minus 1, so it is yn. So here is expectation of alpha n, so So 1/3 alpha n yn. But you know, looking at there, alpha n, you know, yn depends on alpha n. So again, you know, this is equal to 1/3 sigma square alpha, which is 1/3 because sigma square alpha is equal to 1. So let's make it with L is equal to +1. So here I have alpha n minus 1, which is 0. And you know, and the second column is alpha n yn minus 2. Okay, yn minus 2, you know, is 0. So, you know, let's put all the pieces together. So I have a formula where, you know, right here, so that we have in front of us. Is equal to, so I have a -1, 1/3. I have, so it's h minus 1, h0, h1. So it's 1/3, 1, 0. And here the matrix R is Rxx0. Okay, so Rxx0 is 1. Okay, computer for the form. So this is equal to 1, 9, so it's 9 to 8. Okay, so it's a 9 to 8 plus 5. So here I have 5 plus 9 to 8. 5 plus 9 to 8. 5 plus 9 to 8. Along the second diagonal, I have so along here I have Rxx0. Along the second diagonal, I have Rxx1. And Rxx1 is, okay, so it's 2 plus, so Rxx1 is 2 plus 9 divided by 8 multiplied by 1/3. Okay, so it's a 3/8, so it's 16 plus 3 divided by 8. 19 on 8. So it is 19 on 8. Okay. Oh, this isn't only that. 19 on 8. Then I have 19 on 8. And then I have 19 on 8. Then the last one is Rxx2. And Rxx2, this disappears. So there is only, you know, the autoregressive. So for Rxx2 is equal to, so it's 1, 9, 9 goes away, it's 1, 8. So 1, 8, 1, 8. And that's solution. Okay. So now I open MATLAB. Now, there is no need to open MATLAB before. Okay. Now I open MATLAB and I write this matrix, that 1/3 and that, and then I get the solution. The optimum H. Okay? And this concludes the optimum filter. The optimum in the sense that, you know, is the one that solves the quadratic form. Is the optimum in case I know perfectly all the statistical property of the signal. Now we see what is the next question. It's necessary to get that. You cannot make the exercise without doing that. It's necessary to know the statistical property of the signal in case you know. And, you know, it's always advisable to try to get the statistical property of the signal. Once you know that, you can solve it in closure form. If it is non-stationary, then you need to know approximately how it is. Now, what I want you to prove is that h minus 1 is not 0. It doesn't come out to be 0. Because this is going to be 0 only if there is nothing here, which is not possible. And so, this one is not 0. And the optimum estimate of alpha is not the filter that is inverting perfectly this. And the reason for that is because there is a noise. And the noise is correlated. So, if some of you has the calculator, you can calculate the optimum solution. Now, okay, so use 3 samples to estimate the sample as follows. Evaluate the linear MMC estimate of the mean square error. We're done. Okay? That's what we have done. Now the new part. The MSC estimator in C can be implemented in adaptive form by the LMS adaptive estimator method. Okay? So we first evaluate what is the optimum, and then we implement in the LMS way. Now, define the LMS update form. Evaluate the minimum number of steps of LMS algorithm to reach the convergence in mean. Evaluate the loss, if any, in the number of steps to reach the convergence in the mean square. Okay. Now, in order to, so let's solve it. Now, once we have done so much effort, okay, so this is the time-consuming part we have done, okay? So we calculate that. So first, what is the adaptive, so define the LMS update form. What is the LMS update form? Let me go there. Calculate that. So the adaptive says that the coefficient h at iteration k plus 1 is equal to the coefficient h at iteration k. Okay? Now this one is 3 times 1. Huh? Okay? So it's a vector with 3. Tuck, tuck, tuck. So I'm updating all the 3 coefficients. Plus mu. Then here I put the error, the epsilon n, and here I put the 3 inputs. So I need to put xn minus 1, xn, xn plus 1. That's the update form. That's it. Where the error is the error for the estimation of alpha. So the adaptive formula is nothing than that. So now solve for computing the number of steps to reach the convergence in the mean. Now we know that the convergence in the mean, we can say that the mu should be convergence in the mean. Mu should be smaller than 2 times of lambda max. And the time for convergence. Now you always ask me, what convergence should I consider? The convergence with fluctuation or the convergence without fluctuation? No, it's up to you. If you prefer to have a fluctuation, then you say that this mu is equal to these 2 times lambda max, and then you get the convergence. But in any case, the time for convergence, okay, is equal to lambda max divided by lambda min. So what I need to calculate, the ratio between lambda max and lambda min. So what is the ratio? How can I get the ratio? That means that I need to take these matrix, okay? I need to go into MATLAB, and then I write A by MATLAB of the matrix R, which I just computed before. It's numerical, okay? So it's a 3 by 3. You get the 3 eigenvalues. It's numerical, okay? This is by MATLAB. Now, since it's an exercise that I took, some time ago, so I need to see, I go to see, but what are the eigenvalues? Here I was searching other exercises. Once you solve this, what was last year? No, when was it? 6th of February. If you have a MATLAB open, also you can calculate the eigenvalue. Otherwise, I go to the text. July, March. Here. Okay, I order, you see, I can freely decide how to order that. So I ordered the opposite way, okay? Now, the solution, this is a solution. So if I can compute the matrix and I choose H, then what I get is a set of 3 coefficients that are, necessary to get the estimate of alpha. That's because I use MATLAB. Now these are lambda, so let me take this computational lambda and go to our exercise. Okay, these are the 3 coefficients that you get by MATLAB. Okay. So, what is the time for convergence? Okay, the time for convergence is equal to 9.4 divided by 2.9. The time for convergence is larger than that. Okay. So no, because it comes to 3, I don't know, it should be 3 iterations. Okay, 3 iterations. Now, the exercise says, once you got the convergence in mean, I want to see what is the convergence in mean square. And if I put the convergence in mean square, how long does it take? How many steps? Because we know that the convergence in mean square is longer. We need to evaluate how long is that. Okay? So that means that we need to calculate. Now let me go forward theory. So for the convergence in the mean square, mu should be smaller than 2 times divided by the trace of R. That's what the theory says. So let's plug that in. So mu mean square, the mean square error of mu is 2 times trace of R. But this is equal to 2 times divided by the sum of the eigenvalues. That is equal to 2 times, then it's 2.9 plus 5.9 plus 9.4. Okay. So good. So by the way, here I use without I use the convergence without fluctuation. So this is the mu that I'm using. I don't know how much is that, so 9.4, it's 369, 2 divided by 18, so it's 1 divided by 9 approximately, roughly, okay? Just to give a number. So now we need to say what is the time for convergence. Then I go to the book and I see. So the book tells me that in order to converge, where is it? Now the time for convergence, where is it? I didn't compute. It depends on the ratio here. So this is the convergence for the mean, but you know the time for convergence depends on you know, to the maximum time constant, and the maximum time constant is the ratio between 1 over mu and the minimum lambda. So it's 1 over mu to lambda min. So let's go there. And we have is 1 over mu mean square time lambda min. So the minimum lambda is 2.9 and the other is 9. And this is, so it's 1 over, yeah, 1 over 1 on 9. Okay, so it's 9. So, you know, the convergence is 18 approximately. So it takes more steps than before. So how much is the degradation in number of steps? Okay, you know, in a convergence in the mean, I take 3 steps. In a convergence in the mean square, I take 18 steps. Okay, so it's higher, as I expected. Finish. Now, I don't know if you have a question, you know, if you want to revisit something. Otherwise, I go to a new example. Astonishing. Desperate. Too easy, too complicated. I give you another example here. I make an adaptive linear prediction. Now, we will discuss about linear prediction. Okay, we will make it. So I prepared this. We will make about the linear prediction. Okay, so you know later on. But you know, what does it mean, linear prediction? You know, the linear prediction is that I want to predict a certain sample at a time by using the samples in the past. Excellent. This is exactly where, you know, when we started the course, we say, I want to predict, I want to become rich, right? So, you know, this was our philosophy, right? It's a philosophy of the life. We want to become rich. So, you know, we want to invest our money, and we want to, improve or maximize our revenue. Now, so let's see how do I read this equation? Now, I read this equation in the following way. So I have my sample, and this is xn. So this is the n sample, and I'm using all the samples in the past. So this is n minus 1. This is n minus 2, until I have n minus n. So I'm using all these samples. predict that. That's my goal. Okay? So I want to estimate the samples at the position n from all the past samples in the previous positions. So, this one is xn, and we don't know xn. Okay. So this is the estimate. What is the error? The error is xn minus x hat. That this x hat at position n depends on the linear predictor, or the set of the coefficient of the linear predictor. Now, this one is epsilon, and that depends on the set of a linear predictor. So this one is the prediction error. Actually, it's the error, but since it's dedicated to the linear prediction, so I give the name as a linear predictor. The linear prediction error is a prediction error. Okay? So, let's see if I can do it. Well, all right. In order to, I want to find what's the optimum predictor for stationary condition. That's what I want to make. Then I make adaptive. So why do I go through the optimal one? Because I need to have a control of what I'm doing. Okay? So, otherwise you are a software engineer that you implement, but you don't need to know what's going on. You don't need to know what is the limit. So you need to get the optimal solution. You need to have perfect control of the problem you are handling. Now, let's make together. Okay? Let's make together. So, in order to solve it, okay, we use the orthogonality principle. And so we said that the orthogonality principle says that it's orthogonal. The error should be orthogonal. Now, what is the error? The error is xn minus the estimate A transpose xn, set of numbers. Should be, this is the error, depending on the coefficient, should be orthogonal to the input. That's the orthogonality condition. Okay. Now, let's compute it. Let's see what is the shape of the optimum predictor. So I include a new page in order to continue the computation. I recopy the equation. So my equation is expectation of the error, and the error is x minus A transpose xn vector time, I'm simply copying xn transpose everything equal to 0. Now let's continue with that. So I put together this with that and this with that. Now putting together this with that is matrix, this with that is a vector transpose. So let's see what comes out. So I have A transpose, then I have xn, x transpose n. Equal to expectation of xn, x transpose n. Don't make a mistake. Underline means vector. Okay? Now, underline contains xn minus 1 up to xn minus capital N. This is what you know, the vector, this vector contains. No, this is for the unknown. Okay. Now, with patience, let's calculate. So here, you know, by plugging in, here I have x n minus 1, x n minus 2, x n minus capital N. And then I have a row. I have x n minus 1, x n minus capital N. Expectation of. But you know, when I take the expectation for that, now this is equal to xn multiplied by xn, first position. Expectation for that is the autocorrelation in 0. Then I have Rxx0. Then I have xn, and then in the second position, which is n minus 2. Then this one is the autocorrelation in 1. Then the last one, the last is xn minus 1, xn minus capital N, which is the autocorrelation in capital N minus 1. Okay? You know, you can try yourself. These are Toeplitz structure, so you know they are the same. Okay. What are the other? What is this? So we found that one. Now we can find this one. Now this vector is xn multiplied by xn minus 1, taking the expectation of xn minus 1, which is the autocorrelation 1. Then I have xn minus 2, which is the autocorrelation 2, blah blah blah. Okay, so that means that this vector is Rxx1, Rxx2, Rxxn. So interesting. You know, if I put together everything, oh, it's not column, it's a transpose. Okay. So interesting, you know. That means that this structure, the property of this structure, is general because I'm making the linear predictor of order 1. So, you know, sorry, I'm making the linear predictor general. Okay. So what I got for linear prediction, I got this very nice closure form formula, which I copy here. That's the formula that I get. So the linear prediction formula is, I have Rxx0, Rxx1, Rxxn minus 1 is a Toeplitz structure, which means they're all the same along the main diagonal. The matrix is symmetric, so which means everything is here is there, and so on. Okay? So that's the matrix R. This is the linear predictor coefficient is equal to Rxx1, Rxx2, Rxxn. So that one is the optimum. That is the optimum linear predictor. Okay. Now, so this is the optimum means that you have a stationary random process. Okay, so everything is stationary. This is the optimal solution. MMSE, which is minimum mean square error, optimal minimum mean square error prediction. It's a predictor, okay? It's a set of coefficients of the predictor. That's the optimum. Now, everything depends on the autocorrelation, so it depends on the autocorrelation of the signal. Okay, now, how can I transform? Is it clear, I use the orthogonality condition. Tell me.
Shouldn't it be A transpose, or is it just zero?
No, it's A because I made a transpose for all. I already made a transpose. Look at there. There I have a matrix. Where is it? I have A transpose, a matrix R, equal to a row matrix. Okay? If I make a transpose on the right, and make a transpose on the left, I get R. It's R transpose, but it's symmetric. Okay? So I have R multiplied by A equal to a column. That's what I wrote. Okay? Now, so that means that if I know the process, I know that the process is autoregressive, I know that is ARMA, I can design the optimal linear predictor. And this is the linear predictor. How do I make it adaptive? If I make it adaptive, okay, so to make it adaptive, the update equation is the following. So I have a linear predictor at iteration of k plus 1, which is equal to the linear predictor at iteration k plus mu that we are going to establish. The error, the error is, so it's xn minus, it's k, xk minus x hat k, so the predicted value, multiply by vector xk. And this one is the vector. And this is the prediction error. That's the update. The update form. So it's it's relatively simple to implement. In fact, it's one line we will see in a minute. Now I want to show you, I want to say, how do I implement in practice? Okay? Because we will see in the code. How do I implement in practice? Now, in practice, the MMSE, so the mu for mean square error, so the convergence in the mean square error. So the value of mu, we saw that the mu optimum, so mu mean square error, is equal to 2 times trace of R. Okay. Now, so that means that it should be smaller than this. So sometimes, we define a so-called normalized mu. What is a normalized mu? We choose mu such that it is mu0 multiplied by 2 times trace of R, such that mu0 is smaller than 1 in the code. Okay. Now, if I make it this way, it's perfect, because if I choose mu such that is fulfilling this condition, Then if I choose mu 0 that is smaller than 1, then it's it's converging in a mean square. Now this mu 0 is called normalized mu because it's scaled with respect to the mean square error, to the convergence coefficient that guarantee the convergence in a mean square. So that means that we need to compute the traits. Now, a very stupid and simple way to compute the traits is to approximate trace of R by making X and transpose Xn, because that is an approximation of the trace, which means is approximated by the instantaneous power. The power because it's a sum of X n minus, like in a linear predictor, xm minus L square with L equal going to from 1 to n. And so now let's, we can implement in this way by simply computing the mean of all the signal, the mean of the square of all the signal. Now, before the break, I suggest you an exercise. I leave you with an exercise. This is the suggested exercise. You take the intermediate exam, okay? Now, in the intermediate exam, you might remember, at least of those of you that remember. So we have the two random process, alpha and beta. Now, and from alpha and beta, we got three random processes, which is x1, x2, and x3. Now, x1 was filtered by rho, and it's anticausal. That is an anticausal zero filtering, recursive filtering. The second is moving average. The third one, is taking x1 and computing a zero. So, but according to the position of x3, I don't know if you saw the solution, according to the position of x3, the position of the zero is in a reciprocal position with respect to the position of the pole. Then that means that x3 is white. The random process x3 is white. Some of you found it by computation, and nobody got the idea, at least from what I remember. Nobody got the idea that I can compute it without making any analysis. Just from a simple reasoning, at least from what I remember. Now, take a yn. So yn is a combination of these random processes, x1, x2, and x3. Now, you remember there was make a very clear representation of a block diagram. You did it. Characterize the processes 1, x2, and x3. Characterize that, and schematic, blah blah blah. And now, a new suggestion. Now, estimate beta from y. So what I'm asking you is to estimate beta. Now beta is embedded here, so beta is hidden into this after filtering. Okay, so we have this block diagram. So I have beta and let me write here. If I write down, I will. So I have beta n, which is filtered by a filter that is 1 plus z minus z squared. here I got x2. Okay. Now superimpose to that I sum x1 n plus x3 n. This is y. So, considering this new problem, I can estimate beta from y. Now, virtually, you might say, but in order to estimate beta from y, I need to invert this filter. Now, the inversion of this filter that contains 2 0 requires 2 poles. Okay. So the impulse response, even to invert as in the homework. Okay? The homework is not asking you to invert the filter by using some fancy method. You need to simply invert the filter. And you need to remember in the homework 1, that if I need to invert a filter that contains 0 with the poles, in case the poles are outside of the circle, you need to implement by using an anti-causal infinite impulse response filter. Okay, so anti-causal recursive filter. Now, so in this case, if I need to invert these, if I need to estimate beta from y, that means that I need to use a set of coefficients, so a new filter that I indicate here as filter h, and by the filter h I estimate the beta n. So h is my unknown. So what comes out from these exercises that I propose to you is the following. First, compute the optimum estimator. Okay, so the optimum estimator is the one that minimizes the mean square error. So to solve that, use the orthogonality condition. Evaluate the step size of mu. So, for mean and mean square convergence. In other words, repeat the same exercise that we did with this new problem. Now, in order to make this exercise, you need to have the coefficients of the filter. Since the filter is h minus 1, h0, and h1, so probably you need the autocorrection of y computed in 2 delays. And then you need to calculate the correlation between y and beta. And I'll leave it to you. Okay. 10 minutes.